Our next speaker is Song-Young Yi. We're going to continue some of the finite element themes of this morning, and she's going to present some work on a full-field in relation to the Biot model. So, over to you.
Thank you, Don, for the introduction. And it is my great pleasure to be here and be part of the program. Today I'm going to talk about my recent work on pore elasticity modeling. So I'm sure that the pore elasticity is a very familiar concept to most of you, but it is about the modeling of the coupled mechanics and flow in porous media. In other words, we are concerned with the fluid flow in a deforming porous media. Okay? Well, it has many important applications, and the traditional application areas include petroleum engineering or soil mechanics or environmental engineering, and most recently it gains much attention in the biological soft tissue modeling. Okay, so here's the brief outline of my talk. I'm going to describe the model problem, mathematical problem first, and then I'll introduce some conventional approaches. I'll show you the conventional approaches and some issues with them. And I'm going to introduce a new four-field mixed finite element method. And I'll also develop or present four iteratively coupled algorithms. Okay, so here's the Biot consolidation model. Okay, the primary variable here is the displacement U and the fluid pressure P. So the first equation is the mass conservation equation, and the second equation is the momentum balance equation. So here, the C0 is called the constrained specific storage term. So this is a measure of the amount of the fluid flow that can be forced into the soil under pressure, while the volume of the soil is kept constant. Okay, and actually this is the parameter that can cause some issue later. So okay, so remember this C0. Alpha is called the Biot-Willis constant, and normally this is close to 1. K is a permeability, and H is a source function or sink, and lambda and mu are Lamé constants. So these two are describing the mechanical properties of the solid, and F is a body force. Okay. Here, as you can see here, if this alpha is equal to 0, which is not a practical value though, if alpha is equal to 0, then this equation is just pure, transient Darcy flow equation, and this equation is just a linear elasticity equation. So these two equations can be coupled if alpha is equal to 0, but as I said, normally alpha is very close to 1. And this system must be completed by a suitable boundary conditions and initial conditions. And for the boundary conditions, we need two sets of boundaries. The first set is for the flow problem, and the second set is for the mechanics problem or elasticity problem. Okay, so in a certain boundary set, we can impose a pressure boundary condition and some flux boundary condition on the other area of the boundary, and also displacement boundary condition on gamma D, and the stress boundary condition, normal stress, on gamma T. Here, this sigma tilde is a total stress, okay, and it is defined by this. As you notice here, this part is the same as the stress from the linear elasticity, exactly the same, and this is coming from the fluid pressure. And this stress is also called the effective stress, okay? And we can impose the initial conditions. Then now this problem is well posed. Okay, so let me jump into the common numerical approaches. Okay, well, and I'm talking about the finite element method here. So first of all, based on this primary variables U and P, we can multiply each equation by a test function and use integration by parts or Green's theorem. Then you get this weak form. Okay, and what you get here, what you notice here is that our variables are thought in H1 spaces. So U, the displacement, is should be in H1, vector H1, and P should be in H1 space. So you can just use the normal, the continuous Galerkin method, like P1 for instance, continuous P1. Okay. Well, I'm sorry, I should take that back. Well, in this case, this is a mixed method, right? And because this is a mixed method, and we need two different spaces for each variable, these two spaces must be comparable. Okay? In other words, these two spaces must satisfy a certain stability condition, LBB condition. Okay? And if you're familiar with the Stokes problem, you may think that, oh, this vector variable is thought in H1, and also this scalar function is thought in H1. So you can simply try the Stokes stable pair, right? And indeed, we can prove that it works. Okay, if you use, for instance, Taylor-Hood or mini element or RB, then these are actually stable pairs for this method. Okay, but it is well known that if you solve this problem, especially for the pressure using this form, then you don't have the local mass conservation. Okay, so then what can we do? We can introduce a new variable, the Darcy flux Q, which is negative K times the pressure gradient here. Okay, so by introducing this Q now, and this is after we formulate the weak form. So in the first mass conservation equation, you see this Darcy flux variable, and this is the Darcy's law. Okay, but I had to move K to the left-hand side here. And this equation, the momentum equation, is the same as before, exactly same. Okay, so we now have a three-field mixed method, and in this case, this Q and P are thought in H given L2, like in the regular second-order elliptic problem, and the displacement U is thought in H1, vector H1. Okay. Then what kind of discrete spaces can you use? Well, maybe the natural choice would be the stable pair for this Darcy problem and just regular, standard Galerkin method for U. Okay. So here's an example. We use RTK along with PK for the flow variables Q and P. And in this case, this is a discontinuous, the piecewise polynomial. And for the displacement, we use a continuous pk plus 1. Then we can prove that this set of spaces are stable for this problem. Okay? So they are simple. Okay? And especially this one is satisfying the local mass conservation as well. So that's great, but sometimes we have some issues with these two formulations. The first of all, we have some non-physical oscillations in the pressure pressure approximation for a certain set of parameters. Okay, so it's not always. Okay, you don't get these oscillations not all the time, but for a certain set of parameters, and they are this. When C0 is 0 or it's very close to 0, okay, so very small C0 and low permeability, so in other words, small k, and at early times, okay. And we call this a locking in pore elasticity. So let me show you an example. So this is a simple cantilever bracket problem. So we have a unit square computational domain, and I imposed a no flux boundary condition along the all boundaries. And here this left side is clamped. Okay, so this part doesn't move. And here we impose a downward traction. So there's a loading, the downward loading on this top side, and along these two, bottom and the right side, there's no traction. Okay, and I chose these simulation parameters. Okay, I have to emphasize that my C0 is 0, my K is very small, 10 to the negative 7. So in this case, we can expect some numerical oscillations. And I chose the Rabiatoma space, the lowest order, Rabiatoma for the fluid flow problems, and continuous linear space for the displacement. Okay, and this is the pressure profile after the one time step. I'm sorry, I didn't specify the size of the time step. I believe it was 0.001. What you see here is that, I mean, this is a pressure profile, and you might think, oh, there are like two sheets of papers separated. But indeed, this is because of the oscillations. Okay? And remember, our pressure is a piecewise constant. This is the same profile, but we are looking at it from above. Okay? So from different angle. And this checkerboard pattern you see is the indication of the pressure oscillations. Okay? So this is one very well-known issue with these two formulations, two methods. Okay? And another issue is the inaccurate approximation of the stress or total stress. Well, depending on the applications you work on, sometimes the stress variable is really important. Okay? And if you use the previous two-field or three-field method, how do you get stress approximation? You solve the problem, then you have the approximate displacement UH, right? And then you have to use the stress-strain relationship. Okay? So then that involves the numerical differentiation of the numerical solution of the displacement. While doing so, you'll lose the accuracy. Okay? And moreover, even though your displacement is a continuous solution, if the stress that you recovered will be a discontinuous function. Okay? So actually, these were the motivations for my work to develop a new mixed finite element method. Okay, so what I've tried is the following. So I wanted to introduce another variable, that is the total stress. Okay, so I mean the original variables were the pressure and the displacement, and we can add the flux variable for the local mass conservation. Now I'm adding one more, that is the total stress. Okay, and this is an important variable in the pore elasticity. Okay, then the advantage of using this formulation will be the following. Okay, local mass conservation for the flow, and because we are solving for the stress directly, not by post-processing, we'll get an accurate approximation of the stress tensor, or here the total stress tensor. And this will be the possible remedy for locking effects, as you'll see later. And also, when you consider the heterogeneous porous medium, or if you want to model the interaction of the pore elastic medium with a free fluid, for instance, there must be certain interface conditions given, or transmission conditions, and those involve the total stress, okay, among others. So including this will make the enforcement of these conditions much easier. Okay, so then am I the first one who tried the four-field mixed FEM for this model? Well, not really. Okay, I mean, there aren't many four-field methods for the Biot model, but some people already worked on this. For instance, Kursave, or how do you pronounce this? Kursave and Starke, and these people, hopefully they are not here. They used a least squares mixed finite element method. This is a little different from the mixed method that I'm talking about here. They basically try to minimize a certain least squares functional. Okay, so in that, but we are using a little different method here. And in their formulation, they used a stress tensor, but this is not the total stress tensor that like I used, but instead they used an effective stress tensor. Okay, effective stress is from the linear elasticity only. But however, I think that introducing a total stress variable is more efficient because most of the boundary conditions and the interface conditions are in terms of the total stress. So that makes sense. And later, Haga et al. Studied another four-field method, but their primary variables involve these three, Q, P, and U. But then the last one is not the stress variable, but they introduce this minus lambda times the strain of U, or the divergence of U, and they call this solid pressure. I think that this is a common practice in solid mechanics when they study the linear elasticity. I'm not sure how important this variable is in practice, but I personally think that they introduced this variable just for the easy treatment of the numerics. So anyway, so these people already tried some kind of four-field method, but certainly different from what I tried. Okay. Now, before I jump into my four-field method, I have to briefly review the mixed method for linear elasticity because this will be a really important building block for my method. Okay, so here's the linear elasticity equation. Okay, momentum equation minus divergence of the stress is equal to the body force, and this is the constitutive relationship, the law. The stress is equal to some operator C times the strain tensor epsilon of U. Okay, and this is this. And we have to provide the boundary conditions here. And if you plug this expression into here, you get an expression just purely in terms of the displacement. Okay? And then you can drive a weak form based on the displacement formulation. Okay? And here's the equation. And because your solution is in H1 squared, you can use, for instance, the continuous P1, the continuous linear element. Okay, I'm not going to talk about some issues with those elements here because that's not my focus here. Another approach that we can take is to use the mixed method, and especially in solid mechanics, the stress tensor is very important. So we can introduce a stress tensor as a primary variable along with this displacement vector U. Okay, then we still have this equation, momentum equation, and previously I had this form, sigma is equal to C of strain tensor here, but I'm just taking the inverse operator of this here, this side. Okay, so, okay, so A is an inverse operator of C. So I rewrote this problem like this, okay, along with this boundary condition, and I multiply both equations by test functions and use the integration by parts. Then I get this variation of form. Okay, okay, this is a mixed method. So when you find the finite element space, you have to choose the stable pair, right? So and here, what I have to emphasize is that this space is a tensor space, okay? And this stress tensor must be symmetric, okay? And that's what makes choosing the stable pair really difficult because this is tensor H-diff, meaning that each row of the tensor must be in H-diff. But at the same time, this must be symmetric. So you cannot just use two copies of Rabi-Atoma, for instance, because then you don't have a symmetric tensor. So, and this formulation is called the Hellinger-Reissner formulation. It has been introduced like in 1950s or so. But for about more than 4 decades, no one can construct a stable pair for this formulation because of this stress symmetric condition. And in 2002, Doug Arnold and Winder proudly presented their stable pair. Okay, so and indeed they constructed a family of stable pairs for this Hellinger-Reissner formulation. Okay, first on the triangular mesh and then the rectangular mesh, and then but these are conforming spaces, but they have a lot of degrees of freedom, okay, so expensive. So they worked on the non-conforming method, and that's when I jumped into this topic as well, and I constructed non-conforming pairs, and this was my PhD dissertation topic. And later, some other people also worked on this topic. So now we have many stable pairs, okay? But before 2002, there was none. Okay, so now, as explained, we write this mass conservation equation in terms of P and Q, okay, using Darcy's law here. And then I have this momentum equation in, using this total stress. And if this was the effective stress, I would have just this part. But because this is a total stress, which involves the fluid pressure, I have this additional term here. Okay? And based on this mixed form, and also, I had to rewrite this one in terms of the mean stress and the pore pressure because I wanted to have the symmetry, okay, later. So finally, this is the big form of my four-field mixed method. Okay, and as you see here, well, the total stress and Q must be thought in HDiv, tensor HDiv and vector HDiv respectively, and U and P are thought in L2 space here. So as you see here, if you look at this part, this is just a regular, very standard mixed method for the transient Darcy flow problem. And if you look at this part, this is just Hellinger-Reissner formulation. So this mixed method, the four-field mixed method, is actually a coupled mixed method. Okay, so I'm using the standard Darcy flow mixed method for the Darcy flow and the linear elasticity, and I just couple them. Okay, and once you find the discrete finite dimensional subspace of those functional space, then you can discretize this function first in space, then you can get the semi-discrete problem, the continuous in time and discrete in space. Or you can further discretize the time derivative term. In this case, I used the backward Euler. Okay, so this is a fully discrete model. Okay, so now the question is, or the problem is that we have to choose a stable mixed finite element spaces. You just cannot find the random spaces, right? They must be compatible. But as I explained, this method is a coupled mixed and mixed method. So maybe the natural choice would be to choose a stable pair for the flow problem and the stable pair for the Hellinger-Reissner formulation and combine them, right? I mean, that's very natural thing, I thought, but there's no guarantee that if you have a stable pair for the flow problem and another stable pair for the mechanics problem, there's no guarantee that they will be compatible with each other as a whole, right? But luckily, I was able to prove that if you choose a stable pair for each problem, each sub-problem, then as a combined set, they are actually stable. And this will give us the convergent method. So that's what I proved. I mean, just rough sketch of my proof for the existence and uniqueness. I rewrote the problem as a system of differential algebraic equations, and I used the DAE's theory here. So let me skip. I'm not going to go over the details. And I also proved the existence and uniqueness of the fully discrete problem. And here's the error estimates. Okay. For the error estimates, I had to consider two different cases. The first case is when C0 is strictly positive everywhere in the domain. And in that case, usually we don't have any issue. Okay. And I mean, we could use some other pairs, other finite element spaces for each problem, but for this proof, I just chose to use the Rabia-Toma of index K1 and Arnold and Winder of index K2 for the elasticity problem. Okay, if we do so, then we have an L infinity of L2 norm of P, the pressure, and total stress, and the displacement. And also for the flux variable, we had an L2 of L2 norm. Okay, and we got the optimal convergence rates. Okay, and here this constant C1 and C2 are independent of the mesh size H or the time stepping size delta T. How about the case when C0 can be 0 in some area of the domain? Well, in that case, we still have the convergence, but the error should be measured in a weaker norm. So in this case, instead of using the L infinity of L2 norm, I had to use L2 of L2 norm for the pressure, stress, and the displacement. Okay, but in this weaker norm, we still have the optimal convergence rates. Okay, so to test my method, unfortunately for the pore elasticity, because of the complex nature of the problem, we don't have many closed form solutions. Okay, there are only like 2 to 3 about problems available. So this is one of them. This is about the Terjagi's the 1D consolidation problem. So this is concerned with the 1D soil column, and we impose a surface loading on top, and at bottom is fixed, and then the flow is allowed to flow out of on top and bottom. So this we do have analytic form of the solution. So I compared the analytic solution with the numerical solution, okay, as time progresses. Okay, and as you in this case, the solution is not so smooth. Okay, the regularity of the pressure is very low. So instead of measuring the error and showing the convergence rates, I'm just showing this graph. As you can see here, our numerical solutions can reproduce the analytic solution very well over time. And here, this is the same cantilever bracket problem that I showed you earlier, but this time I used the rectangular finite elements. Okay, and this checkerboard pattern is the indication of the pressure oscillations, as I explained before. Now, using this four-field method, as you see here, our pressure profile is smooth, and we can eliminate this locking effect. This example is about the pore elasticity in a layered medium. So we consider the simple layered medium. We have the same material here, omega 1 and 1 here, and in the middle we have a different material, omega 2. So we have different coefficients for the permeability and the Lamé constants. And no flow around here, and then here we have some surface loading here on top, okay, but only in the middle, like from here to here, from 0.25 to 0.75. Then again, we need some interface conditions along the interfaces, and these are the interface conditions, the continuity conditions on P, the normal component of the flux, and U, and normal stress. Okay. And these are some example pressure profiles. Maybe it would be better if I compare these results with the results using the other two methods, because I know that they have issues when they have a big difference in the material properties in the layers. Okay, but I don't have this results, so I'm just showing my results. So what I want to emphasize here is that our method, my method, can produce the pressure without any issues. There was no oscillations, which can be seen using the two-field method, for instance. And when there is a big difference in the material property, like Lamé constants, I still have no problem. Okay. Now, so far we just consider the fully coupled method. Okay, that means that we solve the flow problem and mechanics problems simultaneously. Okay, if you solve the fully coupled method, then it is unconditionally stable and it's accurate. But the problem is that it's expensive, as you can guess. Then what can you do? Well, one thing that we can try is that we solve these two sub-problems in an iterative manner. So we solve one problem first, and then another problem next. Okay, and we keep iterating until it converges. But we hope that the stability and convergence properties are still close to the fully coupled scheme. So I designed 4 iteratively coupled methods. This is a joint work with my student. So they're so-called the drain split, undrained split, fixed strain split, and fixed stress split method. Okay, each of them is based on a different physical assumptions. And I have to emphasize, I have to mention that these are not the first time that we tried this. These ideas or physical assumptions were used in 2-field method and 3-field method widely before, and they were studied. But no one studied these schemes, these ideas on the 4-field method. So here's my attempt. So for instance, for these first two problems, solve the mechanics problem first. Okay, so elasticity problem first, and then they solve the flow problem. These two solve the flow problem first, and then mechanics problem. Okay, in the drain split, when it solves the mechanics problems, it needs a certain pressure. What is it called? Prediction, right? The predictor. And so it lags the pressure variable for one iteration, okay, while solving the mechanics problem. Undrained split imposes a constant fluid mass when solving the mechanics problem. So this doesn't allow the fluid to flow, okay, out of the system while solving the mechanics problem. But this one does. Fixed strain split solves the flow problem first by lagging the volumetric strain divergence of U for one iteration. So this wouldn't change while solving the flow problem. And fixed stress split solves the flow problem by lagging the total mean stress. Okay, in this is a 2D case, but in 3D it should be 1/3 of the trace of the total stress. Okay, this is an algorithm. So maybe I'll just go over this in more details. So for instance, this is how we design the drain split method. Okay, we solve the mechanics problem first, right? And this is the mechanics problem, but I just moved this pressure variable to the right-hand side because this time my unknowns are only this mechanics variables, okay, sigma and U. Okay. And I introduced here the iteration number. Okay? Okay? So we are looking for n, this n plus 1 is a time step, and k plus 1, this is the iteration number. So we are looking for this k plus first iteration of the sigma and u, and we still need certain pressure predictor for this problem. And for here, what do we use? Okay, the assumption under this drain split is that we lag the pressure variable one iteration. So that means that here we just use the previous iteration, okay, for the pressure variable. And once you solve this, okay, now you will have this two, sigma k plus 1 and u k plus 1, and you'll have this. You'll use this information here when you solve the flow problem. Okay, so this is what I meant. So we're looking for pk plus 1 and qk plus 1 using this sigma k plus 1 from this step for the mechanics problem. Okay, and we iterate until converged. Okay, so I mean this just shows the algorithms, but these were derived based on the physical assumptions that we made for each split method. Okay, and so I analyzed these four methods, okay, especially for their convergence conditions. Okay, and what I could prove is the following. So for the drain split and the fixed stress split, as long as C zeros are strictly positive, then regardless of the size of the permeability or the step size, these methods are convergent. Okay? But for the undrained split and fixed strain split, C0 must be big enough compared to CR. Here CR is alpha squared over lambda plus mu. Okay? So when C0 is big enough, then undrained and fixed strains splits were also convergent. So to test my convergence conditions, before I show you the numerical results, I have to mention this. So what I realized is that for the two-field or three-field method, the drained method was only conditionally stable and undrained methods were unconditionally stable. But in my case, the result is switched. So undrained split is conditionally stable, but drained split is unconditionally stable. But for these two other split methods, we still have the same result. Okay? And at first I thought that maybe there is some mistake in my analysis, right? Because this is not consistent. And one of the reviewers raised the question also. But later we realized that, for instance, in the drained method, the idea is that we leg the pressure variable in one iteration while solving the mechanics problem. But when we solve the mechanics problem, we are looking for the stress and displacement at the same time, but the total stress has the pressure in it implicitly. So even though these methods were based on the same assumptions, the implementation of the physical assumption was a little different due to the nature of this scheme. So here's another example of, so this is wildly, this problem is commonly used for the test problem of the polar elasticity problem because we have a closed form of the solution. Okay, let me skip these. This is basically just showing that in all variables, pressure and flux, and later I'll show you the stress and displacement, all of these four schemes could reproduce the exact solution and the coupled solution as well. Okay, and in this case, the parameters, because we know that undrained and fixed strain are only conditionally stable, we chose the variables for which everything just is converted. Okay, so in every variables we see the nice convergence results as long as the convergence criteria were met. And to confirm the dependency of the convergence on the C0, we tested several cases here. So this is when C0 is only 0.5 times CR. So theoretically, from our analysis, we know that only the drained and fixed stress are supposed to converge and others don't, and this is what we see here. Here, yes, drained and fixed stress are convergent, and they converge within much less iterations than the other. But even the others seem to converge, okay? But for the fixed strain, and when K, the permeability is very small, it took much more iterations to converge, but it did converge. And this is when all the convergence criteria met, okay, for each method, okay? And as we expected, all of the methods were convergent. And one thing that you notice is that as K is getting smaller, the number of iterations tend to level off, okay? They're about the same here. And this is when C0 is much larger than CR, okay, 70 times. Again, we expect the convergence for all the method, and they did converge. And here, one thing that you notice is that when C0 is relatively larger, much larger than CR, we see that the drained split and undrained split, their performance are about the same, and the fixed strain and fixed fixed stress, their performance are about the same as K is getting smaller. Okay, and also we looked at the error reduction over the iterations for the first time steps only, and we noticed that for every schemes, after 1 or 2 iterations, the error is just as small as the one from the coupled method. Okay, even though it took about 7 to 8 iterations to converge, but after a couple of iterations, their error was already very small. It was matched to the coupled solution. So based on this observation, what we tried was the following. Instead of waiting until convergence at each time step, we just allowed 2 iterations per time step, and we iterate twice, and we move on to the next time step, and next time step, and etc. And this is this is at time 1, and this is after 1,000 time steps. Okay, so 2 iterations for 1,000 time steps. And as you see here, drained and undrained method could reproduce match the solution from the coupled method very well, even after 1,000 time steps. Okay, but fixed stress and fixed strain are a little off. Okay, these results are not as good as the drained or undrained method. Similar thing happens throughout the whole variable. All variables, like flux variable here, you'll see that these two are a little off in stress and displacement. Okay, but when you allow the 3 iterations, I don't have the result here, but when you allow the 3 iterations instead of 2 iterations, even the fixed stress and fixed strain could reproduce the coupled method solution very well. Okay, so in practice we didn't need to use. We didn't need to wait until the convergence criteria are all met. Okay, so in conclusions, so a 4-field mixed method for Biot model has been presented and shown to have some advantages over the conventional 2- and 3-field method. Okay, so I'm not saying that this method is much better than these 2 conventional methods. Sometimes, depending on the parameters of depending on the simulation parameters or your primary variables, it may have advantages. And also the four iterative coupling schemes are developed, and their convergence results were analyzed. And some computational results were presented to demonstrate the accuracy and efficiency of the method. And we also see that depending on the simulation parameters or the number of iterations allowed per time step, some methods perform better than others. So based on this observation, so we cannot say that one single method is much better than others, but I think that depending on your situation, you can just choose a better splitting scheme. Okay, that's all.
Thank you very much. Questions?
Do you have any sense or any intuition about what's causing this improvement in sort of getting rid of these oscillations?
What was the question?
Why do the oscillations go away?
Okay, so when I published this paper, I was really confident, and I thought that I knew why. Okay, now I'm not so confident, and because later I found out something else. So before my work, Mary Wheeler and Phillips, they published a paper, and so they tried to figure out why these oscillations happened, first of all, to avoid this issue. And they thought that eventually the problem was that the finite element space cannot approximate the divergence of U, the zero divergence. They thought, when C0 is close to 0 and K is close to 0, then eventually divergence of your displacement at time 1 must be 0, but you're not using the correct space and etc. And so I thought that the main issue is to use a finite difference method that can approximate this divergence free, that has a divergence free vector, which is not constant. So I thought that that's why it worked, okay, because in my formulation, U is thought in L2. There's no, and I used the higher order case. But later, I realized that this cannot explain the oscillations. Because if this was the problem, then the oscillation probably would have to be seen in the displacement, not in the pressure. But we have an issue with the displacement space, but then the result is shown in the pressure variable, which doesn't make sense. So I later worked on this, and I found out it's much more complicated. The paper is under review, so I don't know how much I can tell right now. So yes, but for the so now I think that for the three-field method, for instance, this is mainly the issue of the comparability between U of H and so the displacement and the pressure. Once you have a stable pair for the pressure and the Q, the flux. Okay, if they are comparable, these two also must be comparable in some sense. Okay, so now I figured out the reason why this gives us the oscillations in the pressure variable, not the displacement. But for the four-field method, I'm not sure. I just know that this works.
It really works. Sean, would you like to start setting up? There's got any more questions from yeah, while we're having transfer?
So you showed a list of finite elements that work. Which ones did you use?
Oh, so for the convergence analysis, I used RT and Arnold and Winder. But for my computations, I wanted to use a rectangular mesh because that's much easier. So I used a Chen and Wang and Rabia Toma, the rectangular version. Yeah.
Any further questions for someone? Okay, can we just thank her again?
Thank you.